Hi Chem students, let's talk about LeChatlier's principle and this time focus on what happens when the temperature changes. So just to remind you, LeChatlier's principle is all about how a reaction, a chemical reaction, responds to something happening when it's already at equilibrium. So we're going to start with something at equilibrium and do something to it. We call that thing a stress. And LeChatlier says any stress we apply, the reaction will try to undo that stress. So just keep that in mind. Now, why do we care about temperature dependence? Well, that's because our first definition of equilibrium constants was in terms of rate constants. And our rate constants, no matter which one we write, the forward or the reverse, is related to the temperature via, right here, the Arrhenius equation. All right, so what that tells us is if our rate constants, if they're temperature dependent, so is our equilibrium constant. That's the key. Now, it gets a little more interesting because when we change the temperature, then we're not only going to be shifting to undo the stress, but we're going to be changing our equilibrium constant that we end at. So with all the things we've done prior to this, if you put a stress on the system, it would move to reestablish the equilibrium, to create the old equilibrium constants ratio of products to reactants. In this case, it's going to move, but it's also going to create a new equilibrium. So that means we have to keep track of two things. Not only which way it's going to move, but what's going to happen to the equilibrium constant. Will it increase or decrease? So that's where we're going with this. To do this, we really need to focus on two different styles of reactions. And I'm going to start with exothermic. And the reason we're going to deal with this is because if you think about it, temperature and energy are intertwined very deeply. And an exothermic reaction is a reaction that releases energy. So that means that its natural direction is to release energy. All right, so if we have a reaction that's exothermic, something as simple as A in equilibrium with some other substance B, if it's exothermic, then we can write what's called a thermochemical equation, which puts the enthalpy of the reaction as a product. The reason it's doing that is because an exothermic reaction yields, it gives off energy. And that's all we're saying right here is that, hey, this reaction gives off energy. Well, from this point of view now, we can treat energy like a product. And so how would you take a product away? Well, if it's a physical chemical, you would react it or remove it with some device. But energy, we tend to take it, we tend to add it or remove it by changing the temperature. So if we think about it, if I increase the temperature, then that would be like adding energy. And if I decrease the temperature, that's like removing energy. So that means we can easily use the same methods that we learned about before to solve this kind of question. So the question might be something like this. If we increase the temperature for an exothermic reaction, we might ask, which way does it shift? And what happens to the equilibrium constant? That seems like a really good question. So let's answer that. Once again, we're going to use our basic equation here. A is in equilibrium with B just as a way to get around this. And we're going to say that the enthalpy of reaction is the product. All right, so we've increased the temperature. That means we're going to increase the product. It's not really doing this. This is just a shortcut trick that works. So it's like increasing the product. Well, that means we have too much product. How do we undo the fact that we have too much product? We shift left. All right, so if we're shifting left, what does that do for us? Well, our equilibrium constant is related to the concentration of B divided by the concentration of A. When we shift left, the concentration of B will get smaller, the concentration of A will get larger. That means we're dividing a smaller number by a larger number, and that means our overall effect is that our K will get smaller. So our equilibrium constant will get smaller. So the answer to this question is the reaction shifts left to establish a new equilibrium with a smaller equilibrium constant. Okay, let's look at one other example and see if that helps you out. So here's the other example we're going to do. We're going to ask the question, the reaction A plus B is in equilibrium with 2C is endothermic. A, what is the sign of delta H reaction? And B, which way will this equilibrium shift? Okay, if we decrease the temperature. And finally, C, what happens to K? The equilibrium constant if the temperature is decreased. All of those are good questions. A couple of them are pretty straightforward and easy. So let's go ahead and try to answer these. All right, so first off, this is something from 1211. What's the sign of an endothermic process for our delta H? Well, the answer to this is delta H is positive for endothermic. It's greater than 0. So delta H reaction is greater than 0 for endothermic. Remember, endo means energy coming in as an endo. And so if energy comes in, you have more when you end than when you ended. So our change in energy is positive. So how do we handle B? Well, I would rewrite the reaction. A plus B goes to 2C. And then since its energy has to be put in, it's endothermic, I would treat that as a reactant, because it's completely opposite of the exothermic reaction we saw earlier. This time the energy must be put in. Now it says, okay, we're going to decrease the temperature. That means we're essentially going to try to remove a quote-unquote reactant. It's not really a reactant, but it is necessary for the reaction to go. So without it, with less of it, with less energy around, we should see the reaction happen in a different way. So if we remove a reactant, which way do we move? Well, we shift to the left again. And if we shift to the left, what we know is, once again, the equilibrium constant will decrease. So there's our answer here. We're going to shift left, and we're going to decrease. All right, so try to work through this. Make sure it makes sense to you. This is an interesting phenomena that both it shifts and changes the equilibrium constant. So you have to keep both of those in mind whenever there's a temperature change. If there's no temperature change, remember also that the equilibrium reestablishes itself at the old equilibrium constant. There you have it, LeChatlier's principle and temperature changes.